I thank the organizer for keeping inviting me every few years. They invited me the very first time in 1989. And in that edition, only Ron was there and Henry, I guess, and the other, no? And some people in this room were not yet born, I suspect. At that time, I was invited because we had a PRL on the very first calculation ever of piezoelectricity with quantum mechanics. This was a work done with Stefano Baroni and Stefano De Gironcoli. We came, the two of us. And after that, I was kind of adopted by this community. The community started with a strong support by ONR in the person of a very well-informed and scientifically curious officer who supported the workshop and also some of us, particularly in my case, supported all my travel. And we discussed it with David that I regard traveling the most important part of my work. If I sit down in my office browsing the literature, I don't get good ideas. I get good ideas discussing with colleagues, listening to talks. So I like to go to conference even quite often as a simple attendee, not as a speaker, but I came home with something new several times. So you may also notice that I have a new affiliation. And the affiliation is because I'm not as young as I used to be. And in all of Europe, there is the nasty rule of the mandatory retirement age, which our lucky American colleagues don't have. So my friend Roberto Carr, my close friend Roberto Carr, who has exactly my age, has not realized that he is over 70 because there was no transition. Instead, I had a phase transition, so I had to disguise myself as a senior postdoc of the Italian Research Council with no salary. I live out of my university pension, but in order to make research, I have to be a senior postdoc of that institution. Okay, having said that, I think I've said the most important things. Well, over the years after polarization, many other geometrical observables came out, most notably orbital magnetization, but also others. And by now, after almost 30 years from the theory of polarization, I think it's a good time to look at all of them which I know of, which are in some sense related. And you will see that if you look at all of them together, there are several important trends and distinctions. So this is the outline. First, what we define as geometrical. Then I will take two archetypes, macroscopic polarization and orbital magnetization, which they are, if you look at them classically, they are twins. If you look at them as observables, they are very different. And I will tell something more later, but they are different. There is one basic reason, because one is a one-dimensional observable, the other one is a two-dimensional observable at their root, and that makes a huge difference. Then the two archetypes are archetypes of two different classes, and I will investigate the observables I know in one class, where they are defined in modulo 2 pi. I insist they must be defined in modulo 2 pi, and the other they are not, they are exempt. Those in class 2 also admit a density. They are local, they admit a density, and instead in class 1, no. There is no such thing as a polarization density. I don't know whether I risk running over time. Maybe 0.5 with the local nature will be shortened or even dropped altogether, but because I want to be very pedantic on the previous part. And then I have some slides about conclusion, other problems, work in progress. Now, geometrical. Geometrical, you need is not geometrical, of course, in coordinate space. You need to have two state vectors in the same Hilbert space. And then you define a distance, which this is the Bur's distance. Sometimes I use a different one. I don't know. And you have also a phase difference, which is defined in a trivial way. Now, distance is gauge invariant and the phase is gauge dependent. Gauge in this context means simply arbitrary choice of the phase of the state vector. Now, if it is gauge dependent, who cares? Why why caring about that? Of course, Michael Berry showed us that it is important not to forget about that. So even if it is gauge dependent, it's very important. And there is a nice analogy with the vector potential. So you measure vector potential in some point. It's not measurable, it's arbitrary. But the circuit integral of the vector potential, of course, has a physical meaning. So, and this is basically the same. And this is another reason. In classical mechanics, you can always write the equation of motion in terms of the fields. So you have a gauge invariant equation of motion. In quantum mechanics, there is no way of writing the Schrödinger equation without making a gauge choice. Necessarily, the gauge enters the Schrödinger equation. Now, we ask C to be a differentiable function of K. This is non-trivial because in computational work, the phase is erratic. So in general, when you get your vectors out of a matrix diagonalization, you have to do a smart discretization. Now there are the differential distance and differential phase, which are the quantum metric and the Berry connection, which are, of course, like this. And there is a Berry curvature, which is the curl of a connection and also gauge invariant. Those are, notice that the quantum metric is a 2 form, the Berry connection is a 1 form, and the Berry curvature is a 2 form. In mathematical speak, form includes the differential, that is the coefficient of the form and the differential. But we are a bit embarrassed in using that language because we integrate one form in 3 dimensions. Of course, the other 2 dimensions is a non-geometric integration, but and we even integrate, for instance, the metric in 1 dimension. So I will use a sloppy language. I will call form instead the coefficients, and 2 form, 1 form, 2 form, the coefficient, because you distinguish it by the number of derivatives. That is, the 2 form has 2 derivatives, the 1 form has 1 derivative, the Berry curvature has 2 derivatives. I will use this sloppy language. I hope that Joel will forgive me about using this sloppy language, so I will tell form, but instead it's the coefficient of the form, and I count only the number of derivatives. And you can put metric and curvature in the same form, imaginary antisymmetric part, real symmetric part. Now, so much for the single state. So far, the entries have only been state vectors, but we in general, we consider geometric also typical forms in that kind, where also the Hamiltonian enters. And this is the sole legal ingredient to have a geometrical observable. And you may ask why I have a difference. I don't use only the Hamiltonian or only the eigenvalue. Because I want the observable to be invariant by translation of the energy 0. And this guarantees that if I translate the energy 0, the observable doesn't change. Now we do this in block states. We cannot use the psi because they are orthogonal. We have to use the U, which live in the same Hilbert space. All of them are periodic over the cell. So we can do geometry with the U, not with the psi. They obey the HK written in that way. And you see there is a kind of, there is a gauge or a constant vector potential. Now we have many states. We do this in a non-abelian. Non-abelian, here I wrote the formulas. Simply means that you consider the distance between set of occupied states at the same K. So I take all of the states in a band, and this is the distance, and also the phase, consider all of the states altogether, not the single ones. And this is gauge invariant. It means that you can mix the states, the occupied states between themselves, and you get the same result in the gauge invariant case. And also notice that the Berry connection I sum over the occupied bands, insulators only. Instead, metric curvature I sum over can address also metals. Okay, now let's go to archetypes. This is the textbook formula. They are twins. They have the same problem. Is the unbounded position operator. They are dominated by surface contribution, cannot be evaluated with periodic boundary condition. The formulas we arrived at, the one on the top is a famous formula by Kingsmith and Vanderbilt. The second one we arrived in collaboration with David and 2 young co-workers. And when we worked there, we were moved by the analogy. We tried to work by analogy, and then we discovered they are not so similar. Then we discovered they are rather different, and then we discovered they are very, very different. So do they have anything in common? They have nothing in common. The only thing they have in common, they are geometrical, that's all. All the rest is different, because in polarization is defined in insulators only, magnetization, insulators, and metals. The polarization is a gauge-dependent integrand, and magnetization is a gauge invariant. The polarization is the integral of one form, magnetization is the integral of a two form. If you look at the phenomenon of bare bones, P is one-dimensional. You can think even in 3D to have interacting polymers, and you need 2D instead to define magnetization, a stack of planes where the electrons move. Then P is multiple valued. I will insist on that next. And magnetization instead is single valued. Then has been shown in the figure, which I will show again by Ron, if you tinker with the boundary, you can alter the polarization. You cannot do the same with magnetization. And that's the basic reason, because there is a density also. Now, modern differential geometry, mathematicians have discovered long ago that geometrical features in odd and even dimension are very different. That is, if there are four, if you do something in even dimension, you can do something in odd dimension. They're very different. So something happens in dimension 10 and something else in dimension 9. And going down to earth to our small dimensional world, this also concerns us when you look at 2 and 1 dimension. And the Berry connection is a Chern-Simons 1 form. And this is the point. Since our world is three-dimensional, finally, maybe even the Chern-Simons 3 form has a physical meaning, and I will come next to that. But let me explain the bulk value defined in modulo 2 pi. So is a lattice, not a vector. This is a paper I quoted before and contested by Ron. And polarization remains ambiguous until the sample termination is specified. Now, for a one-dimensional system, this is a happy case. There are no depolarization field, there are not metallic surfaces, and furthermore, polarization is dimensionless essentially because it's a dipole per unit length. So if you include in gamma the nuclei, the Berry phase is defined in modulo 2 pi, you have to include gamma in the nuclei, which is possible. If you have a centrosymmetric crystal, you know that P must be equal to minus P. There are two distinct possibilities. Either P equals 0 modulo E or P equals 2 modulo E. These concern two different physical systems, so they cannot concern the same system. This is kind of obvious for those of you who know my single point Berry phase, it's the expectation value over a many body wave function of a unitary operator, and you can put also the nuclei in the unitary operator. If the system is centrosymmetric, must be real, can be only positive or negative, that's all. Berry phase 0 or Berry phase pi. How I demonstrate that this works? This was a paper written for quantum chemists. I didn't like the title, which was shown there, but Kudin said it was more appealing to chemists, so I left the title. And we took polyethylene chains. Suppose first of all, I don't have the plot. Suppose I consider an infinite one in periodic boundary condition, or a closed one. What is the polarization? Well, 30 years ago, I would have said it's 0. Obviously, it is centrosymmetric, it cannot be. By now, I say, if I look only at the infinite chain, it is 0 modulo 1. And to demonstrate that it is 0 modulo 1, we have run the calculation just with the canned code, with the Gaussian code. We gave coordinates, and the code gave us the dipole. Notice that on purpose, we have chosen the molecule, both molecules are not centrosymmetric, only the bulk is centrosymmetric. And you have already seen the plot is this. That means for small length, you have a non-zero dipole, but then eventually you have a convergence to the quantized value. And this shows that polarization really is defined at modulo 1. If I can only access the bulk, I can only see what happens in the bulk. I cannot tell which is the value. And that's the reason why there is not a polarization density. It's not a polarization density. And who chooses the value? Of course, it is nature, which minimizes the energy. Amongst all of the possible quantum possibility, topology is an unbreakable constraint. We know that from the quantum Hall effect. So nature cannot break the constant, only chooses the one which has the minimum energy, which has to do with the ionicity of the groups. It's only one. You can have even more than one. You have to attach a huge reservoir of electrons, very, very, very ionic, and that's all. This is the simple example of Z2 invariant because it is a two-value, 0 pi, 0 or 1. It maps into the additive group of the integers modulo 2. This particular case is even. In other talks, I had a picture also of the odd, but I tell in words. Odd is one-dimensional ionic crystal. Anion, cation, polarization is 1/2 modulo 1. Independently of different ionicity, can be sodium chloride, can be gallium arsenide. You take a chain of gallium arsenide, gallium arsenide, insofar as gap doesn't close. It is topological because you cannot continuously transform an even into an odd without closing the gap and keeping the system centrosymmetric. And some reasons were discovered, topological soliton charge we discovered long ago. How am with the time? But let's go on anyhow. How much?
About 10 minutes.
Okay, fine. Now, this is the extra slide I inserted after the triangular conversation. I've been teaching elementary solid physics for more than 20 years, so I went back to Kittel, chapter 1. And in my mind, I had a sentence, it is an abstraction. Probably was it says, the emphasis is read in mine, the set of mathematical points to which the basis is attached is called the lattice. It says, of course, the lattice points are just mathematical construction. Then it says a primitive cell is a minimum volume cell, and then says there is always one lattice point per primitive cell. So that's enough for Kittel. Then my point is that whenever you have a crystal means that you have a unique way of mapping the real crystal into this mathematical model. And of course, you don't need a density functional solid at zero temperature. You may have quantum nuclei, you may have finite temperature, you may have a solid solution. In all cases, you have a lattice, well-defined and unique. And my claim is that whenever the system needs such construction, then P is a well-defined and multi-value quantum, which depends on the lattice, not on the supercell or of the cell. And in particular, the famous polarization, or infamous polarization quantum is a property of the lattice. So you give me a lattice, and I give you a unique polarization, a unique lattice of polarization quanta. The way to do that for a simple cubic is almost trivial. If it's not simple cubic, you have to do a change of variables, which already is in my review of model physics in '94. Published in '94. Okay, now let's go to 1 and 3 form. In mathematical speak, the electronic term of the polarization is the integral over a compact orientable manifold of the Berry connection, which is a Chern-Simons 1 form. Then mathematicians have defined also the 3 form. It is this ugly and formidable expression. I've seen this expression first time in a slide by David that was, I don't know, made in Berlin, maybe or somewhere else. I've seen that awful formula. Then I went into Wikipedia. If you type Chern-Simons form in Wikipedia, you find very clean and very elegant formulas, very compact in mathematician notation. But if you translate the mathematician notation very compact into our prolix solid state notation, you get that. So this is not an invention by physicists. It's something which came from geometry. And it is a kind of higher order Berry phase. It's gauge invariant modulo 2 pi. And one asks if it has any physical meaning. And some very clever people found it is an axiom term in magnetic response. The cleverest of those people very sadly is no longer with us. So that's some incredible thing. Then there is a much better, much more, this is not an easy read. There is a much more readable explanation in a paper written by David and Joel. Now, this is the table of class 1 observables. We have Chern-Simons one-form polarization, Chern-Simons form axion pair, and all of them all of them are defined only for insulators. The integrand is cage-dependent. The bulk observable is defined in modulo 2 pi in dimensionless units. Their value for a bounded sample depends on termination, and in presence of some protective symmetry, both become topological invariants, as is shown for polarization in 1D. Next, the class 2. Class 2, exempt from 2 pi ambiguity. I've put all what I know of in a synoptic table, which is here. For all of them, the integrand is gauge independent. There is no modulo 2 pi ambiguity. They are independent of termination, and tinkering with the boundary, you cannot change that. Do they emit a local representation? Already see, yes, all of them emit a density. On the same row, we have reciprocal space integral of the same function, imaginary and imaginary antisymmetric, real symmetric. In the first row up, it is simply the Berry connection and Berry the Berry curvature and the metric. So it is the quantum metric. The other are modification of that. Then you may ask why I put all together some rules and genuine ground state properties, because this has partly been said by Joel earlier. If you take a dynamical probe and you integrate over all frequency because of a fluctuation dissipation theorem, this is actually a ground state property, which you cannot measure, as far as we know, with an independent measure, but still is a ground state property which you can express in quantum mechanics as a ground state property. The most important case, maybe if I have the time, I will come back, is the Sousa-Wilkens-Martin sum rule, which diverges in all metals. And it is finite in all metals and measures, for those of you who know what it is, the gauge invariant quadratic spread of the Marzari-Vanderbilt theory of the one functions. So this is a genuine ground state, despite if you want really to measure in a real material, you have to perform a dynamical measurement and then integrate over the whole spectrum. Same for the other sum rule, which is here, magneto-optical. Those on the left are only non-zero for a material which breaks time reversal invariant. Other trends, the odd observables make sense only for dimension greater or equal than 2, obviously, and don't make much difference between insulator and metal. This is something I want to stress. So on the left, you have basically the same formula for insulator metals. On the right, instead, they are different. You see, the Drude weight, for instance, is a non-trivial number for different metals. It is trivially 0 for all insulators. And the one up is, as I said before, is a non-trivial number for insulators. It is divergent all metals. What has to be put here, I don't know. I have a fascinating hypothesis. Since this behavior has much to do with the density of states close to the Fermi level, the real would be that this is only defined for semi-metals, but what? I don't know. The fact that they behave differently in insulator metals has anything to do with the Fermi surface effects. And I will convince you that yes. I write the band projector, that is the projector that projects over the U functions, the occupied ones in both insulators and metals. In any of the forms which enter, I don't like to write them explicitly, but in any of the forms here, since I have, let's say, the integrals must be gauge invariant. There must be two derivatives, so the only way to do that is to consider products of derivative of the two projectors. So one basic integrand should be this. Then there is another operator and the trace. I will not write the formulas, but all of them must have this common ingredient. And now why this common ingredient differentiates between metals and insulators? Because if you write the projector in this way, there is a theta function, a step function, which is not effective in insulators, but in a metal you have a delta derivative at the Fermi surface. And now, when you anti-symmetrize, the delta is annihilated. This is the reason why all metal insulators are the same. They don't care about the singularity at the Fermi level. Instead, the metallic term does contribute in the even cases, as I've seen. Okay, and this is a reference about this part. Then I will move. So I have time also for. What is in the top is a long 50-page review article where there is this and much more. Rivista del Novecento was free online for a short time. By now it's no longer free online. If you're interested, you send me an email. I will send you the paper. The other one instead concerned the bottom line on the table, orbital magnetization through the weight. I wrote a paper in early 17, was rejected in kind of insulting way, so I decided to post on the archive with the comment rejected by physical letters. I will not submit it to any other journal. So I just say I'm rather old man, I don't care quite much to add the one paper. Then I wrote a comprehensive paper about what I said today, essentially, and I sent to Physical Review X, and was rejected with a kind, not insulting, said good paper, but please send to Physical Review B. And I said, no thanks, so the paper is still in my computer, in a deep directory in my laptop. I don't know what to do with that manuscript. Maybe I will do something, but I'm moving on to other interesting stuff. Now let's go to the local. How much time do we have?
You could sort of wrap up in the next minute.
Yeah. So I say you only the principle. I will not show the simulation. The principle is this. Most non-geometrical observables are local. They are meaningful for an homogeneous system. And that means if you know what happens, you can compute this. If you use K, of course, you can only an average. But there is a nice principle by Walter Kohn. The principle applies to the one particle density, but not to individual eigenvalues. So if you have expression in terms of the projector, you can make the bridge. Let's go to the final part. Let me wrap up. So you see I have to cut a lot. Okay. So I've shown what is geometrical means. I specialized to band insulator and band metal, geometrical features, and we published papers about that with two very young collaborators. So then I have something else. This is the table. If you abandon band structure theory and you go for disordered or correlated systems in a different Hilbert space, some of those observables are well defined. The most baffling is orbital magnetization. We don't have a formula. And the Chern-Simons also, we don't have a formula. Well, I go fast. I wanted to say, since I'm running over time, I will not say anymore. Then what I'm doing now, I'm doing some geometrical effect in DC transports. I'm polishing a preprint. I will post a preprint soon. This has much to do with what Joel said. And I also doing orbital magnetization in ribbons, polymer, layered material. I call them hermaphrodite cases. Several years ago, I proposed hermaphrodite wave function, which by now are very popular, but unfortunately our original name was dropped. They no longer call it our original name. The reason why I insist on hermaphrodite is this, of course. You see, it's clear that R-space integration, K-space integration is a good metaphor for this kind of ship. And hermaphrodite brig was a very famous ship. It's the Carnegie research vessel launched in 1909. Okay, and with this, I take your question.
All right, we have time for a question, and can the next speaker come set up, please?
The orbital magnetization to Drude connection. I think of the orbital magnetization as having two separate gauge invariant pieces.
Yeah.
One which, I mean, maybe this is naive, one I think of as more bulk and one I think of as more like edge current.
Yes.
Which one, is it only the bulk part that is related to Drude?
This is very, I didn't want to enter this, but you may have realized, or possibly not, that in the correlated case, the Drude weight is one case up, goes with the magneto-optical sum rule. And if you express in terms of the band projectors, it goes down, is with the orbital magnetization. This is a very subtle point. The fact is that if you convert into the projector form, you have that analogy. If you remain at what David calls the Hamiltonian gauge, in the Hamiltonian gauge should be up. And the many body is like the Hamiltonian gauge. So I don't know if we can discuss privately this. I think it's something most of the audience is cryptic, I would say. Okay.
All right, I think we'll need to move on, but let's thank the speaker again.